Good evening to all of you. I, Ajay Jha, on behalf of ACS India team, welcome you once again to ACS Science Talks session. Just to update you on the upcoming ACS Science Talks, please visit our ACS India webpage and register for the upcoming sessions. We have also updated the ACS Science Talk past lecture recordings into the section of ACS Science Talks virtual library. Please feel free to visit it, like and share among the scientific community. To keep you updated with the scientific research, cutting edge science coming up from ACS journals, the different product launches, we have a monthly newsletter, ACS Insights India. Please visit it, subscribe today for free and enjoy. Now to begin with the scientific session, I would request Dr. Diksha Gupta, Associate Director, ACS India, to introduce Professor Skrabalak and start the session. Over to Dr. Diksha Gupta, please.
Thank you, Ajay, for nice start and sharing so much useful information here. Good evening, everyone. Welcome to ACS Science Talk. We are so pleased to have Professor Sara Skrabalak with us. It's indeed our honor. Sara is a provost appointed James H. Rudy Professor at Indiana University, Bloomington. She has appointments in the Department of Chemistry and Intelligent Systems Engineering. She received her BA degree in chemistry from Washington University in St. Louis in 2002 and her PhD in chemistry from the University of Illinois at Urbana-Champaign in 2007. She conducted postdoctoral research at the University of Washington in Seattle from 2007-8 and began the faculty position at Indiana University. Prior assuming to the role of, I will skip that. So currently she is editor-in-chief of Chemistry of Materials and ACS Materials Letters. Her scientific pursuits lie pretty broad range, and she works on hypothesis-driven approaches for the synthesis of new materials with defined crystal shapes and architecture for application in energy science, catalysis, separations, plasmonics, chemical sensing, and secured electronics. With this brief introduction, I would invite Sara to deliver her scientific lecture.
Well, thank you so much for the kind introduction and also the invitation to speak with everyone today. I am going to deliver a scientific talk on my group's research, but I would like to take the first 10 minutes or so to introduce the journals that I'm representing. In November, I assumed the position of editor-in-chief for two ACS journals, Chemistry of Materials and ACS Materials Letters. And as I'm sure many people in this audience are well aware, Chemistry of Materials is really the flagship journal within the ACS family publishing on materials chemistry. And we're really focused on publishing the latest advances and trying to serve the international material science community. As I mentioned, I became editor-in-chief for the journal in November, and I oversee a team of approximately 20 editors, and their expertise ranges everywhere from energy materials to soft matter to theory and computational science, organic electronics, catalysis. We have a really broad team to make sure that we can cover the entire scope of materials chemistry. A few years ago, we celebrated our 30th anniversary as a journal, which brought on a bunch of new initiatives, which I'll sort of walk through. But we currently have an impact factor just shy of 10. And so a real goal of mine in the next year or two is to push the impact factor above 10. And to do this, I'm really interested in bringing in very high quality, thought-provoking perspectives, as well as reviews, while keeping the journal very accessible for people to publish their primary research. The processing times are relatively efficient, 10 weeks from submission to acceptance. And as I mentioned, we have some different exciting formats for which people can publish. One is perspectives, but within the family of perspectives, which are all by invitation, we have an up and coming series for early career scientists. And so if you or know somebody who might be appropriate for such an invitation, simply send me an email and we'll put them on the list of people for consideration when we send out the invitations. One thing that I find so amazing about Chemistry of Materials was that it really is the first journal that captured how materials chemistry was being published in such a broad area, broad different journals, and really became a home for so many people when it started. And because of that, we have quite a number of papers that have exceptionally high citation numbers associated with them because they were really the cutting edge place to be publishing certain things as new areas of material science became popular. And so we have what's known as our 1K Club, which are which provides editorials that highlight articles that have been published in the journal that have gathered more than 1,000 citations. And we'll have a new 1K Club member being announced in the next month through the editorials. In addition to the 1K Club editorials, we also have just general editorials from that are either invited from the scientific community or from our editorial team. And these are often editorials to help coach you on how to put together effective manuscripts for the journal. So for example, figure size editorials or how to report catalytic results for the journal. We also are specialized in putting together a lot of different virtual issues on particular topics so that you can have sort of a curated list of work from the journal that may align with some of your interests. And we have several of these in plan for the next year. And then beyond the original research and reviews and perspectives, we also offer methods and protocols. And this is really meant to help to improve reproducibility and promote high standards within the community. At the same time, we want to bring new people into doing materials science, and these methods and protocols can often teach you how to do many of the things you might be interested in. They often include videos and step-by-step protocols to get you started in the lab with something new. So if you have an idea, feel free to reach out to me on this topic. But as I mentioned, I'm also editor-in-chief for ACS Materials Letters, and this is a new journal that was launched about 1.5 years ago, and it is a shorter format journal where we're really promoting communications in material science, and it also provides a platform for much more interdisciplinary and multidisciplinary collaborative research as well. So chemistry of materials and advanced or applied materials and interfaces both stopped publishing communications with the launch of ACS Materials Letters. And this has become the home for communications. It is a smaller editorial team because we're currently in the process of growing the journal. But here you can see the expertise that is represented. And this journal also has an editorial advisory board and an early career advisory board. So we're looking for submissions to this journal. But as I mentioned, it's been around for about 1.5 years. We'll have our first partial impact factor announced later this year. But really, we put a focus on high quality and urgent contributions and multidisciplinary and innovative materials research. We also have very fast processing times, typically around 7 to 7.5 weeks. And in addition to the communications or letters, we also welcome reviews, perspectives, viewpoints, and Materials Express. The Materials Express is a really short format article and has been critically important during this pandemic to get some of the research out that is extremely time sensitive. So that is a great avenue for such kind of research. So hopefully that gives you a good sense of the two journals that I'm representing. At the end of my scientific talk, I'd gladly welcome questions about the journals as well as my science. So in terms of the science, I'm going to share with you some of my group's recent work involving the synthesis of multimetallic nanocrystals by design. And I'd like to really start by thinking about the big picture, which is this idea that function follows form. This is really a central tenet of modern materials science and materials chemistry and chemistry in general. And we don't have to look much further than the lock and key model that accounts for enzyme activation to think about the relationship between function and form, where if you have a molecule of a specific shape or form, it can bind into the active site of an enzyme and induce a response or function within the body. So the molecular form or the function follows the molecular shape or form. This same idea that function follows form extends into the realm of material science, where we could consider, for example, low density polyethylene versus high density polyethylene, where the degree of molecular cross-linking or molecular form can influence the resulting mechanical properties that are going to be displayed by the resulting plastic. And so the same idea that function follows form also extends into the realm of inorganic nanomaterials, where we could start at the most basic level and consider the crystal structure of our material, where the crystal structure and the bonding type that holds the material together is going to determine whether or not it's going to be a conductor versus a semiconductor versus an insulator. But moving to longer length scales, the nanoscale, the form of our material can refer to a number of different parameters. For example, we can consider particle size, where if we decrease the size of an inorganic crystal into the nano regime, there's going to be an increase in the surface to volume ratio. And this can make for more efficient use of precious materials and applications that require the surface, such as catalysis. But completely new properties can also emerge with decreasing particle size. For example, the light scattering and absorption properties of metals can depend on particle size. You're familiar with gold in the bulk having a lustery yellow color, but at extremely small particle sizes may appear red or other colors to your eye. In addition to particle size, particle shape is important to the function displayed by metal nanocrystals. We can consider, for example, a face-centered cubic metal such as platinum, palladium, or gold, and when prepared as a nanocube, it will selectively express what's known as the 100 facets, which have an open packing arrangement of atoms, in contrast with when the exact same metal is prepared as an octahedral nanoparticle. In the case of the octahedral nanoparticle, this will selectively express the 111 facets, which have a close packed arrangement of atoms. These differences in atomic arrangement can give rise to different surface adsorbate interactions, and in turn, different catalytic activity and selectivity. Also, the light scattering properties and many other features will depend on particle shape. So again, example of how the form or the function of our material follows the form that it takes. We can also consider the overall architecture of our nanomaterials, where I'm referring to the three-dimensional arrangement of different components in space. So it could be something that has a core shell architecture or a multi-component material where the spatial arrangement could influence the overall function that it displays. And while I won't really talk about it today, we could also consider the mesoscale, where now we're looking at how the spatial arrangement of nanoscale building blocks influences their spatial arrangement relative to one another, how that influences or brings about new function. So there are many beautiful examples of how the form of nanoscale materials can influence their properties and in turn their ultimate utility in a variety of different applications. However, if you were to actually do a Google search for this phrase, function follows form, what you will find is that the inverse relationship, form follows function, pops up way more often than function follows form. And the reason for this is because of a famous American architect named Louis Sullivan. In his book called The Tall Office Building Artistically Considered from 1896, he put together a way of thinking about the construction of a modern building. And the idea that he's so well credited for is that you would never go and build a building without thinking about how people are going to use that space and what their intended function of that space is. And so you only ever start the construction by thinking about how people will interact and use that space. And thus form ever follows function. And so with this point in mind, I put forward the following idea, which is, could we achieve nanomaterials by design? That is, if we understand the size and shape dependent properties of inorganic solids, it should be possible for us to identify specific nanomaterials that would have the properties that are ideal for a particular application. But a major bottleneck in realizing this idea of nanomaterials by design is that we simply don't have the synthetic tools that allow us to achieve nanomaterials with the necessary precision to then actually go and use them in applications as predicted based off of their predicted properties. And so it's in that context that my research group is really trying to provide the synthetic tools so that we can achieve nanomaterials by design. And we're especially interested in trying to come up with pathways to increase the complexity of nanomaterials while preserving precision because of their size, shape, and compositional dependence on properties. And to do this, we have been using seeded methods as a platform to build more complex nanomaterials with precision. And the reason why seeded methods are so powerful is because the barrier for heterogeneous nucleation or seeded nucleation is much lower than that of homogeneous nucleation. So if you have a predefined nanoparticle in solution, you can anticipate that the deposition of additional material will occur preferentially on that structurally defined seed rather than having homogeneous or free nucleation in solution occurring. So as an initial demonstration of the real versatility or value of seeded methods came with our demonstration of seed-mediated co-reduction as a route towards shape-controlled alloyed nanoparticles. At the time, about a dozen years ago, it was quite challenging to achieve shape-controlled alloyed nanoparticles, but you can start to imagine how this may be beneficial in applications such as catalysis. So you could start with, for example, shape-controlled octahedral seeds and co-reduce gold and palladium salts using ascorbic acid in the presence of a capping agent such as CTAB, and you can transfer the shape of your initial seeds to a core shell structure where the surface or the shell is an alloy composed of gold and palladium. And shown here is the product from this synthesis where we have the octahedral nanoparticles anticipated because of selecting octahedral seeds. And from our elemental mapping by STEM EDS, we have gold and palladium mixed in the nanocrystal at the surface. And this alloy composition was also confirmed by powder diffraction. So this was a nice way of increasing the compositional complexity using seeded methods. And it turns out that the seed-mediated co-reduction approach is quite versatile, where we can access a variety of different shapes in addition to the octahedral nanoparticles. For example, in addition to octahedra, we can have cubooctahedra, nanocubes, and even 8-branched octopodal nanocrystals shown here on the left, or here's a reconstructed tomogram of a single particle where you can see the 8 branches of these nanocrystals. These different nanocrystal shapes are achieved by simply changing the reaction pH or the amount of palladium relative to gold in that deposition step. And the reason why we're able to access all these different shapes is because these very minor changes in our reaction conditions changes the rate at which metal is depositing on our seeds relative to surface diffusion. So at fast rates of deposition, we end up with more kinetically favored structures such as the branched nanocrystals, where the atoms get stuck at their initial deposition spot. Whereas at slower deposition kinetics, we end up with more thermodynamically favored shapes such as the octahedra or cubooctahedra, because now the atoms can diffuse on the surface to find their most thermodynamically favored positions. But one thing that I would really like to bring forward is that even though we have all these different shapes that are being accessed by these minor changes in deposition kinetics, they all have octahedral symmetry, just like the initial seeds that we were building the nanocrystals on top of. So seed symmetry is being transferred to the final bimetallic nanocrystals. And this really becomes a general principle with many seed-mediated synthetic approaches, where if you select a seed of a particular symmetry, you can transfer the symmetry to your final nanocrystal. So we demonstrated this idea by selecting seeds with a variety of different symmetries. Here are cartoons of palladium nanocrystals with octahedral D4H, tetrahedral D3H symmetry, but different shapes. And if we do the fast deposition kinetics that favors branch formation, we can always end up with branched nanocrystals as our product. But the specific shape that's going to result depends on the underlying symmetry of our initial seeds. So from octahedral shaped seeds, or seeds with octahedral symmetry, we always ended up with branched nanocrystals with octahedral symmetry. But switching to palladium bars, which have D4H symmetry, we end up with branched nanocrystals, again with D4H symmetry. From tetrahedral symmetry, tetrahedral symmetry. From right bipyramids with D3H symmetry, branched nanocrystals with D3H symmetry. Looking at this a little further, you'll notice that we have many more branches, or many different numbers of branches. And in the first 4 cases where we're growing off of single crystalline seeds, we have all of the branches are proceeding along the 1-1-1 directions. So the different number of, and the branches are emerging from the vertices of our seeds. There's a slight variation with the right bipyramids. Right bipyramidal seeds have a single twin plane that bisects the nanocrystal into 2 single crystalline domains. And so we end up with 2 axial branches proceeding in the 1-1-1 directions, but then the equatorial branches have the twin plane that continues into the branches and proceed along the 1-1-2 directions. But looking at all of this, it gives us some general principles of how we can think about the growth of metal nanostructures, where deposition will occur preferentially at the vertices under kinetically controlled growth conditions or fast deposition to facilitate branching. And the branching will occur in the 1-1-1 directions in the absence of twin planes. But we can put all this together to create crystals with different hierarchies. So one question that I've often received when presenting these results is, well, what happens if instead of building off of convex nanocrystal seeds, what happens if you grow off of concave nanocrystal seeds, such as your branched nanocrystals? So for example, we could select our 8 branched octopodal seeds and grow off of them, but we have a choice. We can select conditions that favor slow deposition and the formation of more thermodynamically favored morphologies, the polyhedral shapes, or a pathway at higher reaction pH where the deposition rate will be much faster, and we tend to favor more kinetically favored structures. So considering this further, we can now see the effect of reaction pH on the resulting nanocrystals. So metal deposition is occurring preferentially at the 8 tips of our branched nanocrystals, but under slow deposition conditions that favors the thermodynamically favored shapes, we end up positioning polyhedral or octahedral shapes at those 8 tips. In contrast, we end up with multiple branches proceeding in 1-1-1 directions from each vertex of our branched nanocrystal under fast deposition conditions. Now we have 2 new nanostructures that we can then build on top of, and each one of those has 2 different paths, the slow deposition path or the fast deposition path. And so we can continue forward. Now at this point, we get a little bit of crowding, but you can still see the general trends that at fast deposition conditions, we end up with many branches that are emerging from each of the many different tips of our initial seeds. Whereas under the slow deposition conditions, we end up with more polyhedral forms forming. But here you can see we've just sort of increased the size of the polyhedra here, whereas now in this version here, where we have so many different growth positions, we create or initiate many more smaller polyhedra. So when my student Josh was working on this project, we actually tended to refer to this as the snowflake project, because the crystal forms are a bit reminiscent of snow crystals, and the overall mechanism is quite reminiscent of how you end up with these beautiful hierarchical and highly symmetric crystals of water. Whereas ice begins to crystallize in our atmosphere, you'll end up initially with a hexagonal shaped seed that forms in the upper atmosphere. And then that hexagonal crystal carries that provides the overall symmetry for your snow crystal, just like our nanocrystal seeds do. But then you end up with these variations of different sort of undulations in your snowflake, because the snowflake, as it's passing through the atmosphere, is sampling different conditions of pressure and humidity. So that is different supersaturations, which you can think of as different rates of deposition, just like we did chemically with our metal nanocrystal system. But in nature, it's occurring simply by changing temperature and humidity and pressure. So I think it's a really beautiful example of how you can have inspiration from nature and take that and apply it to your own systems to bring about increasing crystal complexity in nanomaterial synthesis. So one thing that we've been particularly interested in more recently is the idea of how can we impart regioselectivity and chemoselectivity in seeded syntheses. So hopefully I've convinced you at this point that you can introduce greater compositional complexity and achieve quite complex nanocrystal forms with precision through manipulation of the growth kinetics and control of seed symmetry. But you can start to imagine how maybe you want to position a new material in a particular location or modify an existing nanocrystal selectively in some way. And if you want to achieve that goal, you need to have tools that impart regioselectivity and chemoselectivity. In this context, actually looking back at this original system gave us some of our initial starting places where we would look at these right bipyramidal seeds. For example, with these right bipyramidal seeds, as I mentioned, there's a single twin plane that bisects the right bipyramidal seeds into 2 single crystalline domains. And what that effectively means is that the axial vertices are crystallographically different from the 3 equatorial vertices that contain that twin plane. And so when I have presented these results in the past, I would often get questions along the lines of, well, are all 5 branches the same in length? Or do you get faster growth kinetics from one type of vertex versus another type of vertex? Unfortunately, it was difficult to answer that question because the particles always tilt in the electron microscope. And so you can't really effectively measure the branch lengths in the axial and the equatorial positions very efficiently. But it did inspire us to think about, could we take advantage of these crystallographically inequivalent sites to achieve regioselective growth? So the basic idea or hypothesis behind this was that at very low supersaturation, we may be able to force a choice between these crystallographically inequivalent sites because the barrier for heterogeneous nucleation on the axial positions may be different than that of the equatorial positions. So you can imagine then taking these right bipyramidal seeds and decreasing the amount of metal that's available to deposit so that you can enter into a regime of low supersaturation. And what we found is that there was a preference for metal deposition to occur at the equatorial positions of the seed rather than the axial positions. And you can see this in the elemental mapping shown here after deposition, where we were depositing gold on top of our palladium right bipyramidal seeds. And you see that there's gold all along the perimeter, but you don't see any metal really at the center of the structure that's indicative of gold deposition in the axial positions. So we were quite excited by this initial demonstration of regioselected overgrowth in seeded syntheses. And it led us to think about a potentially more challenging question, which is whether or not these conditions of low supersaturation could be used to force a choice between crystallographically identical sites. So for example, if we were to look at a nanocube, we have 8 different vertices, but they're all crystallographically equivalent. But you could imagine for some application, it may be desirable to selectively deposit metal just at one vertex or at a few vertices rather than all 8 vertices as we observed in our initial demonstration. Now you may wonder, well, what would be the actual driving force or reason why at low supersaturation, you may be able to achieve such selectivity? And this is where the imperfections of nanocrystal seeds and nanocrystals in general may actually be an attribute or something that we could exploit. So shown here is a transmission electron microscopy image of one of our nanocube seeds. And when you first look at it, I think, oh, it's incredibly beautiful. There's such high monodispersity in the sample. But then if we start to look at it at the single particle level and examine it closely, what you'll notice is that the degree of curvature is quite different in some regions of the seed. So for example, I think it's most evident right here that the curvature here is a lot different than, for example, here or here. And these differences in curvature could mean that there's a different barrier for metal deposition at each one of these vertices. And so at very low supersaturation, we may be able to force a choice between those types of crystallographically identical, but at the atomic level, different sites. So in our initial experiments, we took palladium nanocubes and deposited gold. And as you go down a column, we have increasing amount of gold relative to the number of seeds in solution. And as you move across a row, we have increasing sodium bromide concentration. The sodium bromide was added to the synthesis to passivate the surfaces of our nanocubes. Bromide is known to absorb strongly to the 100 faces of palladium nanocubes. And our thought being that could help passivate any sites on the faces that might be susceptible to metal deposition, making the vertices more favored for deposition at high bromide concentration. So I know that if you look at this big grid, you really can't see what's going on. So I'm going to pull out 4 examples to walk you through. So the first one is where we have a low bromide concentration. So we should have very little bromide on the 100 faces, which would allow for deposition on the faces of the cube. We also have high metal concentration, so we shouldn't anticipate much selectivity. And indeed, we end up with conformal growth and core shell nanoparticle formation, as shown here. Now we can change to low bromide concentration, low metal concentration. So the low bromide means that we have the faces are available for metal deposition in addition to the vertices, but there's not that much metal available. So it may force some degree of selectivity. But what we found is that we just really had diffuse gold islands sort of all over. Now at high bromide concentration, low metal concentration, now we're blocking those 100 faces and making the vertices more favored for metal deposition. The low metal concentration, though, we're at low supersaturation, that may force a kinetic choice. And what you find is that instead of all of the vertices ending up with metal deposition, we have metal deposition just occurring at a few of the vertices. So some regioselectivity is being achieved. And then at high bromide concentration, high metal concentration, we end up now with the faces being well passivated, so metal deposition should occur at the vertices only, but because we have such a high concentration of metal precursor, that selectivity for one vertex over another has disappeared, and we end up with metal deposition occurring at all of the vertices. So here's a cartoon that sort of summarizes the major trends from our experimental data, where you can see that surface passivation and supersaturation work together to provide some degree of regioselective overgrowth. One thing I will caution is that we do have some mixture of products at every position, but the general trends hold. So I'm hoping that with some refinement, we may be able to achieve even better selectivity. So for the sake of time, I'm not going to go through some of our most recent work on trying to achieve chemoselectivity, but we do have a recent perspective in Dalton Transactions that talks about regioselectivity and chemoselectivity in nanomaterial synthesis that I would encourage you to check out if this is a topic of interest for you. In the last minute or two that I have, I did want to just touch briefly on some of the properties of these nanocrystals. I've been talking exclusively about how do you make them, but of course we are interested in their properties and potential applications. So one thing that is exciting is that these branched nanocrystals have well-defined localized surface plasmon resonances or light scattering and absorption properties that we can tune throughout the visible and into the near infrared as a function of their size and composition. But one thing that's quite remarkable is that when adding palladium to these gold nanocrystals, we end up with incredibly high sensitivity to changes in refractive index compared to all gold nanocrystals. And this is inherent to the introduction of palladium in low concentrations to the gold platforms. And so this is opening up possibilities for chemical sensing based off of changes in refractive index. But one of the other major challenges with using gold nanocrystals in plasmonic applications is that often they're structurally unstable. They undergo deformation or changes in shape during storage, during heating, just being left in solution. it turns out that if you add a small amount of palladium to gold nanocrystals, that they can impart much greater thermal and structural stability. And this is represented in the data shown here in the bottom, where we worked with Sara Skrabalak's group at the University of Antwerp to study the heating, the morphological changes of our nanoparticles when they are heated within an electron microscope. And we did a study where we compared our gold palladium octopods to all gold octopods. And what we found is that if you have all gold octopods of the same size and shape, they will evolve into more spherical morphologies between 200 and 300 degrees of heating. In contrast, if you have added palladium to the structure, there are very little changes in morphology until 600 or 700 degrees. This is an incredible improvement in the thermal stability of these nanocrystals. And so you can see how you have some evolution of material from the tips with a small radius of curvature into the body of the nanocrystals with heating. But these large deformations shown down here are not occurring until around 600 degrees or higher. And so that makes them incredibly robust photothermal agents, which we recently reported in collaboration with Luis Liz Marzan's group in nanoscale, where you could look at these branched nanocrystals for photothermal applications, and they preserve their photothermal response and are quite efficient over very long periods of time because of adding just that small amount of palladium, 10% to the overall nanocrystal. So with that, I'll come back to really the big picture, which is this idea of achieving nanomaterials by design. I think with our synthetic tools, we're getting closer to realizing this vision where you could imagine using, for example, some sort of computational tool to predict the optical properties of a nanocrystal, and then selecting seeds of an appropriate shape or symmetry and the appropriate deposition kinetics to build off of them to predict a specific type of nanostructure that you might be interested in studying, and then going and making it directly and intentionally. And so that's really my broader vision and why I get really excited about coming up with new chemical ways of making complex nanomaterials with precision. If this topic interests you, I want to draw your attention to a book that I recently wrote for the ACS in Focus series, which is all focused on metal nanocrystals. It's meant to be an introduction for people that are new to this area of research and talks about fundamentals of metal nanocrystal formation, as well as their properties and other considerations. And with that, I'd like to thank you all for your kind attention. I have an absolutely excellent group of students who did all of the work that I shared with you today. Without them, this just simply wouldn't be possible. So I'm forever grateful for them as well.